quiz questions on rotational motion. How many radians per second is 25 revolutions per minute equivalent to? One revolution is 360 degrees or 2 pi radians. Therefore, 25 revolutions would be 25 times 2 pi. But that is in a minute or 60 seconds. Therefore, if you divide it by 60, you will get it in a second. Now remember that frequency is 25 rotations per minute, and that when you divide by 60 becomes rotations per second, and then omega, the angular velocity or angular frequency, is 2 pi times f. So 2.6 radians per second is the answer. And look at the unit of angular frequency is radians per second. So that is how you convert 25 revolutions per minute into radians per second. So that there is a very important equation to change linear frequency into angular frequency. The second one, a wheel of diameter 26 centimeter turns at 1500 rotations per minute. How far will a point on the outer rim move in 2 seconds? Okay, so in this case you have to find how far it moves. So you are trying to find the displacement or the distance moved. Now that's the diagram, that the radius is 13 centimeter. And it's turning at 1500 rotations per minute, and you're asked to find this distance in 2 seconds. Okay, so that's what you're trying to find, for which we'll try to find the angle first. The frequency is 1500 rotations per minute, which is 1500 divided by 60 rotations per second. That's 25 rotations per second, and like in the previous question, omega is 2 pi times f. So that gives 2 pi times the frequency 25, 157.1 radian per second. And because omega is v by r, and that's again another important relation from which you rearrange. Make linear velocity the subject. You know that omega is 157.1. Multiply with the radius, and you get 20.42 meter per second as the velocity. And now distance is velocity multiplied by time. So 20.42 multiplied by 2, because you're asked to find the distance in 2 seconds. And you get approximately 41 meter. A wheel of radius 1 meter is rotating with a constant angular speed of 2 radian per second. So that's omega. You can see that. That's omega because it's given in radians per second. What is the linear speed of a point on the wheel's rim? So you're given omega and you got to find the linear speed v. And the relation is omega is v divided by the radius, from which you can calculate the linear speed as the product of r and omega. The radius is 1 meter, omega is 2 radian per second, and you get 2 meter per second as the linear speed. Fourth one, a wheel accelerates with a constant angular acceleration of 4.5 radian per second squared. If the initial angular velocity is 1 radian per second, what is the angle the wheel rotates through in 2 seconds? The angular acceleration is represented by the symbol alpha. Look at the unit, it's radian per second squared. So it's not omega, it's alpha. The initial angular velocity, that's omega naught, is given, and you have to find the angle the wheel rotates through in 2 seconds, and this is like using the king in linear motion. Omega 1, the initial angular speed is 1 radian per second, alpha is 4.5 radian per second squared, time is 2 seconds, and you have to find theta. What's the relation between this? This is theta is omega 1 t plus 1/2 alpha t squared. So that corresponds to the king in kinematics, right? Same thing. One times 2 plus half times 4.5 times 2 squared. Gives 11 radians as the angle. A wheel of diameter 68 centimeters slows down uniformly from 8.4 meter per second to rest over a distance of 115 meters. What's the total number of revolutions the wheel rotates in coming to a rest? So what's given is the velocity, the linear velocity initially, and then finally 0, distance is x, 115 meters. So the radius is half of 68. Write down the given quantities, that's in centimeters now, and you know that the circumference is 2 pi r, and that will be the distance rotated in one revolution, right? The distance moved in one rotation is 2 pi times the radius, which we get as 2.14 meter. Now the question says that it moves over a distance of 115 meter. So if you divide 115 by 2.14, you are going to get the number of revolutions, because the distance moved in one revolution is 2.14. So when you divide that, you get 53.8 as the number of revolutions. Quite easy. The sixth one, the bolts on a car wheel require tightening to a torque of 90 Newton meter. If a 30 centimeter long wrench is used, what is the magnitude of the force required when the force is perpendicular to the wrench? Now, torque is given by the product of the distance, the perpendicular distance, and the force. Now rearrange that. You get the force as torque divided by the radius, and that gives 90 Newton meter by 0.30, which gives 300 newtons as the answer. The seventh one, a wheel with moment of inertia 300 kilogram meter squared has a net torque of 3.5 Newton meter applied to it. What is the angular acceleration? Direct question again. Moment of inertia, I, and the torque given, you have to find alpha. The relation is torque is equal to I times alpha, and rearrange, alpha is tau by I, so divide the 3.5 by 3. 1.17 radian per second squared. A 4-meter long rod is hinged at one end. The rod is initially held in the horizontal position and then released. The free end is allowed to fall. What is the angular acceleration? Okay, a diagram. That's the rod. It's 4-meter long, hinged there, and it's falling. And its rotational inertia is ml squared by 3 given, which in this case is, because the length is 4, just 4 squared is 16, so you get 16 m by 3. Alright, now what you see there is the weight acting vertically down through the center of mass. The weight acts through the center. And the torque is given by I times alpha. Therefore, alpha is tau by I. And the torque is the product of distance and force. The force is mg. Alright, the distance is mg, and the force is mg, and the distance is 2 meter. Why 2 meter? Because it's half the distance. Look at that. The pivot is here, and the force is acting here. So the distance is 2 meter, isn't it? And so the torque is 2 times mg. So plug that in here. 2 mg divided by what we got for I. The masses will cancel out, and when you plug in the numbers and calculate, you get the answer as 3.68 radian per second squared. A rotating flywheel can be used to store energy. If it is required to store 1 times 10 to the power 6 joules of energy when rotating at 400 radian per second, what is the moment of inertia? Again, direct question, because kinetic energy of rotation is given by 1/2 I omega squared. Kinetic energy of rotation is 1/2 I times omega squared. And rearrange to get I is equal to 2k by omega squared, and kinetic energy is given as 10 to the 6, omega is 400. Substitute, you will get 50 kilogram meter squared. And in this question, a solid sphere of mass 1 kilogram and radius 0.01 meter rolls with a speed of 10 meter per second. So it is rolling, and how high up an inclined plane can it climb before coming to rest? So this is the sphere trying to roll up, and assume that it reaches till here. So what happens is its total kinetic energy at this point decreases as it goes up and gets converted into potential energy. Therefore, whatever kinetic energy it had here at the bottom will change into potential energy at the top. And the kinetic energy at the bottom is of 2 types. Because it's rolling, it has it has rotational kinetic energy, and its center is moving forward, so it has linear kinetic energy. So the sum of the two is equal to the potential energy at this point, right? And again, you can substitute for omega as V by R, and I is 2 by 5 mr squared. That's the moment of inertia or rotational inertia of a sphere. Cancel the masses throughout and the radius squared from here, and then you get 7 by 10 V squared is GH. Rearrange that to make H the subject and calculate to get 7.1 meter. Brings us to the last question. A figure skater rotating at 5 radians per second with arms extended has a moment of inertia 2.25 kilogram meter squared. If the arms are pulled in so that the moment of inertia decreases to 1.8 kilogram meter squared, what is the final angular speed? This is a case of conservation of angular momentum. Conservation of angular momentum. That means I1 omega 1 is equal to I2 omega 2. When the arms are pulled in, the moment of inertia decreases. Therefore, the angular speed increases. Substitute those numbers, I1 and I2 and omega 1, and you get 6.25. So you see that the angular speed increases from 5 to 6.25. So look at these problems and try to prepare for the exam. Thank you.